Yeah. Okay, let's begin. We're going to jump into Bayes factors and model selection. I say model selection, but what I really mean is hypothesis testing. And so model selection is oftentimes a hypothesis, two competing ideas. And so, for instance, is the intercept zero in a regression model? So that's one of those setups where you're doing the sharp tests. And so all of this can be extended not to things like, let's say, xi's were distributed normally with mean mu and variance sigma squared, and maybe you want to test if mu is equal to 0. I don't want to dwell a lot on those sort of examples because I think that they're ridiculous. So just estimate mu. Tell me what you think mu is, in that sort of context. We will write that down just because we can work through the math and understand what's going on. But I want to scale this up to something like model selection. So I don't think that's a real question. Is mu 0? No. It's something maybe close to it or something like that. So you want to quantify that. The difference in what I would say model selection, where you have, y is equal to x transpose beta. You've got a whole bunch of these little beta coefficients. Potentially you could have thousands of those or millions of those. Even 10 would be a lot to think about. And so you might want to just say which ones are reasonably close to 0 and just throw them out of the equation. That I don't need those to explain the whys. And so it's just too much for a human to think about all at once. I think in that context it can be a useful tool even though you're doing the same sort of thing. So I'm going to try to build you up in that direction. You have to do something in those cases. But I don't think we should be always talking about is mu 0 or is p 0.5 in a Bernoulli model. Because the answer is no, it's just what is it? And since that's a one-dimensional thing, you can just kind of think about it. What would I do? I'd draw the likelihood. If somebody didn't want to be a Bayesian, and then I'd tell them about regularizing their likelihood and what the boundaries could do. And so I do something like that. Say, I think p is somewhere over here, or mu is somewhere over here, and I would explain that to them. And if somebody asked me to hypothesis test on it, I would say no. And I have said it. It was a long time ago, but I was writing a paper and one of the journal editors came back and said, whoever your statistician is just seems to refuse to do hypothesis testing. And in that case, I was, yeah, good, bravo. You're right. In this problem, I do refuse to do it. So there's been a lot of attention surrounding hypothesis testing and some of the quirks that can happen. And what I want us to do in this class is maybe learn how to use that in examples where it is applicable, where you got to do something anyway. You got to think about what you're actually doing and know how it compares to other procedures as well. So we'll try to do that. But I also want us to understand all those nuanced differences between the different paradigms. So it's very hard to understand something just on its own, but comparing to something else kind of gets context. So we'll be spending some time dwelling on this. I put a few links up on the website. We'll look at these in a moment. What I'd like to do is take a moment to go over the midterm. So I have some scores right here. And that's what they are. So that's our data in some sense. These are your test scores. I will hand these back to you at the end of class. And I will ask, if you don't like your test score or whatever, and you want to argue about it, wait until Friday. So take it, look at it, digest it, think about it. You can compare it to your friends or whatever. If you think I marked you off 2 points too many or something like that, or they got an extra point and the answer is really similar, I'd say don't let that bother you so much. But if it does bother you, we can talk about it. I did go through this a couple times, the exam, and so you'll see like your score scribbled out, and I always added something to it. So after I went through the exam, after 3 sessions of grading, I went back through, looked at everything, and I tried to give you guys a little bit of inflation. And I do that every time. So it's not that bad. You could fix this in like a minute. And so, but at first it kind of irritates me a little bit more, but then I started thinking about how much work would it be for you guys to fix the problem. And so that's also what I want to give you the opportunity to do. If you redo the midterm, So you'll just write down on a sheet of paper or something like that. I'm not going to give you my text file for it, but you'll just write down all your solutions or whatever. So type it up reasonably, cleanly. If you don't have time to type it, make sure that it's highly legible. And I'll give you something like 50% of the difference between your scores. So people that already did really well, I get it. I totally get this. It's like, I don't have the opportunity to get as many points on this. I used to hate that. You know, where it's like, I have a 97, and the most I can get is now a 98.5. Come on, man, I want to get like at least all 3 of those points. So don't let that stuff bother you. So everybody has an opportunity to learn in this class, and that's what it's really about. So it's not about crushing your competitors. So we don't think about it that way. I used to think about it that way when I was an undergrad, but it's just really a poor philosophy. So everybody should do well and try to learn this stuff. I'm not going to be giving you back the regraded midterm. What I'm going to do instead is I'm going to look at your grades at the very end, and then I'm going to pick up your pile of extra credit, including your midterm, and I'm going to look at it, and then I'm going to score it if you need the points to go higher. So that's how I'm going to approach it. So try to do a good job. I think I've already given you the solutions. I've told you how to do it. I will tell you again if you need to, but I do want you to write this stuff down because it's going to help you learn. And that's the point. Okay, so there's our scores. Looks pretty good, right? Any questions? We don't look at data like this. You know, just a column of data. So it's not very helpful. I could put it in a table if you wanted. It's not going to help you. So you guys are statisticians. Yes, please.
So when are the redos due?
Yeah, let's do a week and a half. So redo exams. I'll say due in 10 days, whatever that is. What is today, the 3rd? So that's the 13th. Is the 13th, you have a calendar, right? Is that a Monday, Wednesday, or Friday?
Saturday.
It's a Saturday, of course. So 14th, 15th is a Monday. So I'll say 12 days. 15th, November. So that's a rule I have, that anytime I come up with a date for something and it lands on a weekend, it's always due in the next class period. So if I ever write anything down wrong with a date like that, you can just assume. Patrick.
So then on that, I noticed that the homework is due the 16th.
Yep.
Oh,
yeah, so I answered your question already.
17th.
Do it on the 17th. That follows the rule. I do that all the time. I don't know why. So I grab a date, I miscalculate it real quickly. I don't look that carefully. So I'm just kind of ballparking the 2 weeks anyway. And I don't get hung up on these things. So I don't like living my life strictly by a calendar or watch. So sorry, that's just important. Cool. And that rule is always true in all of my classes. Okay, anything else you want to know about the midterm? Jay?
What is the average?
What is the average? Okay, so this is, exactly, let's do some stats. The mean. That's the most common thing, right? I don't know if it really applies here. I'm not sure why you're asking for the mean. I would start arguing with you as a statistician. Is that really the right way to look at this? But 74. Any other questions?
How's the skew?
How's the skew? Let's look at the kurtosis of everything. Have any better questions?
What's the histogram look like?
What does the distribution look like? That's what you always want to know. You don't want the mean, you don't want the variance per se. Before you even think about any of those things, you'd want to know about what the distribution looks like. So Peter's interested in outliers, yanking that thing over. That's what he's thinking about. That's why he asked about the skew of everything, the third moment, essentially, and it measures skew. So what does the distribution look like? I think that's what we really want to know. Looks like that. This is what I want every single time. Somebody gives me something I want to see. Histograms have their own problems. So I can't quite tell what distribution that is. I will say this, in all of my classes that I ever teach, it's bimodal. It's always bimodal. That's why the mean isn't a great number. So, and I could argue with my old professors about that sort of thing, that if there's 2 standard deviations above the mean, you get an A, that sort of stuff. That is just nonsensical. So, violation of like imposing normal theory. That's normally distributed. So what would happen is if I ended up looking at the average of your scores year after year after year after year, that would be normally distributed. But that certainly is not normally distributed. Central limit theorem doesn't apply to your distribution in this class. What else do you want to know? This is kind of a horrible way to look at the data too, because it's like, what is this? I will say this. Obviously, there's always a couple people up here that always do really well. I've seen lows lower than this. So this isn't my most astonishing low we've ever seen. So this is all kind of normal. I usually see more multimodality. And so I like to look at this a little bit different. And this is what I'm going to do when I grade your everything and put together all your work and assign grades. So I'll just say, let's do one more plot. Everything. There's the scores in a different way. So all I did is I sorted the scores, and then I just plotted them against the x-axis. Inadvertently, that's actually a QQ plot for a uniform distribution. Because if I think about the uniform, what's the cumulative distribution? It's x. So if I break that into the quantiles, it's a uniform spacing on the x-axis. I plot your scores next to it. So it is a QQ plot compared to the uniform distribution. It certainly looks uniform to me. So that's at least my eyes. What I mean is it's close enough to be uniform that it's like, that is really weird. Usually there's these bigger jumps. So for instance, that thing right there, usually I'm looking for big breaks in everything, and I can draw the line right there. That's not a very big break. That's pretty small to me. It's not uniform, and probably a test would reject uniformity, but it looks roughly uniform. And I can kind of see where the deviations from uniformity exist, where those gaps are big. That's kind of interesting. So I would say there's not a lot of obvious places where I can draw the line on these grades, but I will say probably something like, what I'm thinking is maybe somewhere around here. Everything to the right is probably an A. So I kind of give you, my prior says your grad students working hard, probably get an A. People to the left of that, you're more in the B range. I'd be inclined to say everybody in this class could get at least an A minus after looking at this. So if you can improve, pick up your midterm scores, kill it on the final, then I think after I average everything together, you'd probably be around an A minus. But we'll say this, if you crush the final and you crush all the rest of the homeworks, I'll give you sympathy, so as well. So I have all these different grading scales. And what I really think about is, how do I get this person to an A or an A minus or something like that? And if I can't, it's not my fault. So be thinking about it that way. I want you to be as successful as possible. So again, this is all training, but by the end of the class, we should know this material relatively well. Hopefully the midterm is kind of outlined what we're missing. And if you did well, congratulations. Sorry for the lecture. Anyway, okay, so maybe somewhere around here, you're like, oh, I feel a little bit safe. But if you're right here, and I didn't cut my cursor on that number, and you're like, oh, I'm right there. Don't worry about it. You're in the same boat as this other person. And so if I do come up with a grading strategy and it picks somebody up and it moves them across somebody else, I pick them up too. So if there's something somebody did, one of my mercies, and all of a sudden I'm able to elevate their grade from a B plus to an A, anybody else, I look at them too and I see how they did, and I probably pick them up to an A too. So you guys can look at my grading. I try to be reasonable. So it's not about that again, it's about the learning. Anything else you want to see? I think that's kind of it. So what's the skewness? All the mode is 70, the median in this was like, I don't remember, 76. So not heavily skewed. Kind of interesting. Any other questions? Let's look at a few things. Let's look at our course webpage. So there's a few statements in here. There's a statement from a couple different journals. Some of you have heard me talk about this before. I never really get tired of pointing this out. But back in, when did this happen? 2015, so a while ago, but not too long ago. And this happens every couple of years. The editors of BASP, so this is the Basic and Applied Social Psychology Journal, made a pretty powerful statement. So the Basic and Applied Social Psychology BASP 2014 editorial emphasized that null hypothesis significance testing procedures, to give it a name, is invalid, and thus authors would not be required to perform it. However, to allow authors a grace period, the editorial stopped short of actually banning null hypothesis testing. So I'll just say Neyman Pearson testing, because what they're really saying is the P less than alpha. So P dumps alpha, you set alpha to be like 5%, the typical thing, and you just do that and you say, hey, this is statistically significant, and you're just pushing that forward, they'll chop you from the journal. So that's what they mean when they say null hypothesis significance testing procedure. They mean Neyman Pearson, P dumping alpha. We'll talk about what that is if you don't know, and what the theoretical guarantees are. There's no real guarantees in life though. So following the statistical modeling assumptions, then there's some mathematical statements we can make. It's a little bit rough. They say that it's invalid. There's validity to it. It's just, do you want to use it? So we have to understand what they actually said in the first place and what it is. I think that it would be fair to say that it's been wildly abused. And so that's a fair statement. It's wildly abused, it continues to be wildly abused, yet people still keep using it. I'll say this will be the black eye of statistics, the field of statistics for hundreds of years to come. That'll be my statement, is at least the way that we've advocated using it. The purpose of the present editorial is to announce that the grace period is over. From now on, BASP is banning the null hypothesis significance testing procedure. So I bet these guys are fun. With the banning of the null hypothesis significance testing procedure from BASP, what are the implications for authors? So people ask, will manuscripts with p-values be rejected automatically? No. So they'll ask you to remove it eventually. What about types of inferential statistics such as confidence intervals or Bayesian methods? Confidence intervals suffer from an inverse inference problem that is not very different from that suffered by null hypothesis statistical testing procedures. So if you do the pivoting sort of thing, and you come up with your p-values that way, what usually your interval tells you is the range of values that you wouldn't reject. So the values that won't produce a p-value that's less than alpha. Then it tells you everything outside of that. So that's what they're saying is the inverse thing. That's not the only way intervals are formed, but the pivoting procedures do lead to that. And so if you want an example where that's not exactly true, the Bernoulli is a good example. The reason why is the question of how do you compute variance. There's only one parameter there. I'll let you think about it. Still similar. So I guess maybe suffers from a problem that's not very different. I guess that's about right. So they say they're not going to accept that either. They write a few statements. I'll let you read through them. They go on to talk about Bayes. So Bayesian procedures are more interesting. So I really don't like their language, to tell you the truth. It's like interesting. Like say something specific. So everything's interesting. So that can't be what they mean. The usual problem with Bayesian procedures is they depend on some sort of Laplacian assumption to generate numbers where none exist. The Laplacian assumption is that when in a state of ignorance, the researcher should assign an equal probability to each possibility. This kills them, too. So they're wrong in both areas, unfortunately. They're saying you have to come up with a prior. That's not a problem for Bayes. That is Bayes. So what they're saying is the Laplacian procedure is to assign flat prior to everything. Nonsense, we don't do that. So card-carrying Bayesians, I would like to see their cards. So don't do that by default. So we don't just assign, and we're not putting numbers where none exist. We're weighting something, and it's going to have some inferential property. I would agree that Bayesians make you think about everything that needs to be thought about when doing a test. It's just sometimes it's very difficult to make certain choices. We'll talk about that as well. So they say you can do some Bayes. You know, there's been some Bayesian proposals that at least have somewhat circumvented the Laplacian assumption. There's been a lot of stuff that's happened. And there might even be cases where there are strong grounds for assuming that the numbers really are there. It's just crazy talk. But these are not statisticians. They're people that are applying something, and I guess they're talking to their community. Consequently, with respect to Bayesian procedures, we reserve the right to make case-by-case judgments in thus Bayesian procedures are either required or neither required nor banned. Every single thing that an editor does should be a case-by-case decision. You know, you should be able to think about all that. That should apply everywhere. It should probably even apply to the p-value thing. I have a question. Why do you think that BASP, these are social psychologists, so sociologists, psychologists, why are they making the band? Why are they the ones that are coming in and ruffling everybody's feathers? Any idea? You know any of these guys? You know what they do? A lot of p-values. So a lot of them just do, I don't know anything about stats, so I'm just going to do this thing. It's auto procedure. So I think that's part of the answer. I think there's another part of the answer too. What does their sample size usually look like? And where does it come from? Where do they get their samples? Huh?
From people.
They get them from people. How do they do it?
Surveys?
Usually surveys. So all our PhD friends that are in psychology are writing some survey and sending it to zillions of people. Minus the low response rates, which heavily bias things. We don't like surveys with low response rates, and there's a ton of this stuff. They can usually get N really big. And so usually they ask like some sequence of questions. They want to know if two groups are the same or something like that. N is huge, and they find out the two groups differ a bit. And I could have told you that was going to happen. You could play this game forever. If you just do things slightly, there'd be some difference, but it's not, maybe not a meaningful difference. Maybe they're just a little bit apart from each other. And as N gets really big, you'll be able to detect them. Now, if you're a physicist shooting particles and you wanted to know, is there a little bit of energy given off by some little particle, that small whisker of difference and not being like 0 or something, no energy, maybe that's meaningful. And so you have to think about how big the scale is. Maybe it's really close to 0, how much energy a particle has, or how much force it emits. It's very hard to detect, but you want to be able to say that it's non-zero. So somebody came in the last couple of years and said, there's new particles and new forces that exist. And people didn't believe it, but no surprise. I bet there's even more out there, but they just have such small contributions that it's hard to measure them. That's a case where maybe a p-value and huge N just keep smashing particles. It would see something, a little bit of flicker of light, and hey, it's not 0. That means something exists. For a lot of questions that we're answering, like maybe is a coin flip 0.5, if it was 52% or 48%, we wouldn't really care. We do it all the time. So coin flips are not 0.5. Probably if it were a random flip in the first place, you probably want to pick tails. So I think they come up a little bit more often, about 52% of the time. Do we care? Nobody cares, because we always let flip a coin. And usually in cases where we're like, let's flip a coin, we don't really care in the first place. It barely matters to us. Like, which movie are we going to go see? So, Titanic or Star Wars. Okay, in that case it matters. Okay, there was another article that came out from the ASA, and they've kind of revised this a couple times. I want you to read through it just to know the state of the field. Ron Wasserstein gave a talk here in the last few days on this, and I've heard him talk about this a lot. I don't know if he gives prescriptions. Statisticians, you put them all in a room and they'll just argue with each other. In February 2014, George Cobb, Professor Emeritus of Mathematics and Statistics at Mount Holyoke College, posed a question to ASA discussion forum. Why do so many colleges and grad schools teach P equal to 0.05? And I think what they mean is if alpha is equal to 0.05 and if P ducks it, then you reject. So I will give him credit because he knows what he's talking about, but he probably phrased that just a little bit wrong. Because that's still what scientific community and journal editors use, is the answer. Why do so many people still use P is equal to 0.05? Because that's what they were taught in college or grad school. And so we'll at least try to put a dent in this here, in this class. We're not teaching it to use it, per se, but rather we're teaching it so that we understand what it is. It is important to get it if so many people are using it. There's a lot of interesting quotes in here. The problem is not that people use p-values poorly, we wrote, it's that the vast majority of data analysis is not performed by people properly trained to perform data analysis. That's a rough thing to argue probably, and that's hard to quantify in itself, so how would we even quantify that? So, anyway, you can read through this, but this is a thing that is definitely a sore spot for me and for a lot of statisticians. So we're going to understand what Bayesians do and what non-Bayesians do as well. Okay, I also put a homework up, and there's a problem in this homework that I'd like you to think about. First part of the homework is the wrap problem. I want you to code up that Gibbs sampler. So you'll code that Gibbs sampler up for all of these full conditional distributions. I want to point out, I didn't ask you to write down the full conditional for alpha I, beta I, because you know it. It's right here. So in your Gibbs sampler, you also need to update those parameters, the random effect parameters. You don't put a prior on anything because they're already random. And so you'll need to update all of these parameters. You'll also need to update that as well. I didn't ask you to work this out because it's written down in the model for you. It's nothing to work out. Okay, I also want you to implement your Gibbs sampler for the Cauchy regression problem. So I can turn this distribution into a Cauchy by averaging over these gamma half-halves, where I'm averaging in this particular way, where I'm rescaling the scale parameter. So it's a scale mixture model. So I had to generate data that looked like it was Cauchy, has some sort of correlation structure. Can't quite call it a correlation structure because there's no covariance, there's no variance in Cauchys. And so this is the scale matrix. So if it were a T3, that would be a correlation. I want you to basically just implement this Gibbs sampler. So you'll be updating the gamma i's, the betas, and the p's. And so I'll point out that this beta update does involve generalized least squares formula. So where the covariance matrix is the diagonal of all those gammas. You can work that out. We'll do a review session next week on Wednesday, so if you have a lot of questions about this stuff, that'd be a good time to go over it. And I'd be happy to go through details that you might be missing. Here's an interesting problem. What we're going to do is we're going to generate a bunch of xi's. And this will help you to understand the difference between a Bayesian and a non-Bayesian for testing. I'm going to assume you all know how to do the two-sided p-value test. You look at a normal distribution, and you know what the standard error is, and you can compute that p-value. If you don't know how it works, you definitely have never taken a stats class before, because it seems like it's indoctrinated into us. So I'm going to assume you know how to test various hypotheses. So I let theta be my mean in the distribution. What we're going to do is we're going to sample from a mixture model, meaning that some of the times the theta is 10, some of the times theta is 15, some of the times theta is 17, and some of the times theta is 20. I didn't make those probabilistic, but if you did make them probabilistic, that would make it a true mixture model. But I'm going to have you generate 400 of the x's with theta is equal to 10, 200 with theta is equal to 15, so on and so forth. So you have 1,000 xi's. Now, this is a mixture model, and we'll be talking about mixture models later, how to do this correctly. But I basically want you to see that if we test the wrong hypothesis, how a Bayesian and a non-Bayesian differ. And so I'm going to ask you to actually do something that you shouldn't do, but you do see people do this all the time, and it'll help to highlight what the difference between the two groups are. I think in this, the non-Bayesian is the winner in some sense. Okay, so you'll have 1,000 things from these different mixtures. I want you to scramble them all. So scramble everything, shuffle it, so it's not just in order. And then I want you to consider each one of these hypotheses. So I want you to test basically these various hypotheses. So theta is equal to 10. Okay, if you were to compute your p-values for that, you would know how to do that. I'll teach you how to compute the posterior probability of this. When a classicist is kind of asking this question, theta is equal to 10, they're asking, is it that number? They don't really care about the alternative so much. They just want to know, is it 10 or is it something different? And the Bayesian is going to baseline things a little bit different. It's going to say your universe of values is 10, 15, 17, and 20. And they're going to tell you which answer is closest to looking true. Those are very different things. So I want you to write down a Bayes factor. I'll tell you about those soon for all of these. And then I want you to make some plots. Basically, I'm going to make you plot is a function of the sample size, what the p-values look like. Okay, so I'm going to have my vector of 1,000 data points. So there's x1000 in here, here's x1 right here. So this is 1, this is 1,000. And so I want you to compute the p-value for all of these. So this might be for h naught, theta is equal to 10. And so for the first data point, I want you to compute whatever the p-value is. I'm going to say you know the variance and everything. You're going to simulate this data and you know what it is. So you can use the known variance. So even with one data point, you can do this calculation. Then you're going to maybe the p-value's up here. So maybe they live between 0 and 1. So maybe the p-value's here. And then on my second data point, right here, the p-value maybe is a little bit smaller. Then for the third data point, maybe the p-value jumps around. So you're using the cumulative of all this. So this right here uses 3 data points. That uses 2 data points. That's 1. That's what I mean plotting the p-values in sequence. And then maybe after everything, you notice that your p-values are kind of decaying. They're going small. Something like this. So for this problem, all the p-values should be decaying. For the Bayesian answer, since we're going to be computing posterior probabilities on everything, one of them will be climbing to 1 and all the other ones will be decaying towards 0. So for the Bayesian, when you compute the posterior probability of everything, there's going to be all these different hypotheses. So theta is equal to 10. This is going to be theta is equal to 15. This is going to be theta is equal to 17. This will be theta is equal to 20 right here. And you'll be coming up with these posterior probabilities. Probability of h naught given all of your data. You'll have that on all of these axes. Turns out one of these is going to be climbing to 1, and all the other ones will be going to 0. If you do this correctly, for any given number, right here, let's say this is like x 500. I have that same number right here. If I go to that point on my graph and I add them all together, they should add to 1. Because Bayesians are computing a posterior probability on something, and it has all the properties that posterior probabilities have. P-values do not do that. And so for all the p-values, they'll all be decaying towards 0. And basically what the Neyman Pearsonian doing this would be saying is that none of those thetas look right. They're all wrong. And they would be right, because we're going to be testing theta is one value when it's not actually a value. There was a mixture model. So we're making a faulty model assumption, assuming that everything came from one normal distribution. Bayesian's going to say, based off of all your choices that you have, they'll try to give you which one they think is closest to the truth. And that evidence gets stronger and stronger and stronger in a comparative fashion as n gets bigger and bigger. So totally different things. So Bayesian is going to force you to think about the alternative very carefully. When they give you a posterior probability on the null, it's being directly compared against the alternatives. So it's a comparative measure. Fisher, when he was coming up with p-values, and he was advocating maybe if p is small, you reject, he's saying something different. He's saying, I don't know what the truth is, I'm just saying that's not it. So it's very different than saying, out of these 4 truths, which one do you like best, versus you just want to reject them all. Danielle?
Would you mind explaining again why all 4 of those should sum to 1?
I will explain it in the future lectures.
Okay.
So, but it's because the posterior probability is going to be on H naught, and this is going to have different values, and there's only going to be 4 values. So we'll see it when we get to what Bayes factors are and how to compute these posterior probabilities. I still need to tell you about all this stuff, but this will at least get you started. I want you to at least understand what the Neyman-Pearsonian is trying to do, or what Fisher was advocating is just this contradictory, set up this contradiction paradigm. It doesn't look like that. I don't know if that's the right thing to do. I think you have to think about what you're comparing against. So, in my life, I've thought about many times, is it possible for me to just say that's not true? I just know that's not true, but I have no idea what the answer is. And I don't think that's true. I think I compare it against all my experiences in life. And I'm always making that comparison. So Bayesian's going to force you to mathematically define it and write it down. That's probably what I think is more interesting for Bayesian, is how they make the comparisons, what the comparisons mean. Okay, a few other homework problems. So heads up for the next homework. I want you to write down the mixture model that you should have used to compute the Bayes factors. You don't need to think too hard about this, because I'll tell you what it is before this is due. And then I want you to compute some other posterior probabilities on the null. And I want you to prove that under the null hypothesis, a p-value has a uniform distribution. I need to tell you about a lot of stuff. Let me start out by telling you what a Bayes factor is. And this is kind of the bread and butter for Bayesian testing. We will be going into classical testing as well, so we can make all these comparisons. So Danielle, great question. How do you do this all? It'll take me a couple days. So lots of controversy surrounding what we're about to do. And I'll be telling you about those controversies, and I'll be demonstrating the controversy as well. Well, let's just start out. Bayes factors. So this is what it is. So we're going to compare 2 models. So this can be a lot of different things, and I'm going to write it down generally. But this could be something like mu is 0 in a normal model, or it's something different. Those would be 2 competitive models. It could be maybe the intercept in the model is 0, or it's something different. These can be nested hypotheses. They can be pretty much anything. So this paradigm will at least encapsulate all ways you can compare models. It's one thing I like about this, that it's general. So I'm going to say H naught is one model. So here's my null model. And this is my competing model. In some ways, Bayesians are paying equal attention on both the alternative and the null. It's not entirely true. And in some ways, the non-Bayesian, or at least the Neyman-Pearsonian, p ducking alpha, they're overemphasizing the importance of the null and not spending enough time thinking about the alternatives. I'm going to write this out generally. I'm going to say theta, and these are my model parameters. These are going to live somewhere. And I'm going to write this down like this, H naught. Some space. So maybe this is like the space in which, if we were thinking about an example, maybe theta represents the mean of a normal model. And so this maybe contains, I'm saying theta is equal to 0. So it lives somewhere. So this is the space that it lives in. The alternative, theta is going to live somewhere else. I'll write down H1. So sometimes people will call this the alternative. And this is going to be some other space.
Is that union a capital theta?
That's what it means. That's my version of capital theta. Circle with an H in the middle is what people accuse me of it looking like. I guess it does look like that. Yeah, this is just some other thing. So it could have been smiley face and frowny face. But some other space. We'll start generally and then I'll escalate to some examples. So, and I'm going to say where theta, this is going to be the entire space. It's going to be the union of theta naught, theta h naught, and theta h1. Union. So maybe these are sets or something like that. So theta lives in this space. So that's the domain for theta itself. The valid areas where theta can live, and I'm breaking it up into these two things. So I union these two things together and it's the entire space. I should also probably say that there's no overlap between these two things. So theta h naught intersect theta h1 is null, i.e. the complement of theta naught, theta h naught, is theta h1. So it'd be set up really badly. I'll say that's complement. If I were trying to compare against two things that were really embedding the same thing in both spaces, so we need to separate them. Okay, so we've got some notation. Let me tell you what a Bayes factor is. This is the notation I'll use for Bayes factor for obvious reasons. It's going to be this ratio where I'm going to take the integral. I'm going to look at my likelihood function on theta. So same notation that we always use. And then I'm going to have some prior distribution on theta right here. But I'm going to say this prior is specific to the null. And I'll need to give you examples. But this is going to place mass on this space right here. So it depends on how I want to place mass in that space, but this is going to be the prior specific to that. And I integrate. And I'm going to compare it to the likelihood. And I'm going to have some prior on the alternative, d theta. Where am I integrating? I'm going to integrate in my null space. And I'm going to integrate in my alternative space. So I'm just comparing these two likelihood functions where I average them differently. So it looks like a Bayesian setup. I've got prior, I've got likelihood. So in some sense, this has something to do with the posterior measure. I'm averaging over it. And so I would say that this is comparing the averages of how well the models fit in these two different spaces. So hopefully you see this as an averaging and an average. So it's basically on average, how well do these two model classes support the data that we've observed. So my interpretation of this number might be something like this, is comparison of how well the data, that's X, supports the hypotheses. H naught and H1. And I'll say on average. So what you're really doing is you're just averaging over the two different model classes and comparing them. So if this number was greater than 1, it'd be leaning in the direction of the null hypothesis. If it were less than 1, it'd be leaning in the direction of the alternative hypothesis. Now be careful when you're writing down your Bayes factors. Sometimes people flip these upside down. You're talking about the wrong equations with people in your head. I've had that conversation where I'm like, that's not the equation. Oh, you flip it upside down. It took us 45 minutes to get there. I've had that conversation. Very frustrating. Here's another measure. There's something similar. Similar measure looks like this. We're going to take the likelihood functions. I make a comparison, but instead of averaging, I'm going to look at the maximum value. Theta is in theta naught. I'll just write it like this. Theta H naught, so it looks the same. I'm going to take the maximum in my alternative space. And I'm going to compare them to each other. Who's seen this before? Lots of people. So what is this called?
Likelihood ratio?
Yeah, it's called the max likelihood ratio statistic. You have to turn it into a test. But yeah, close. So this is the max likelihood . And what Stephen knows is that Neyman Pearsonians are using this in disguise. So in thresholding this and then calibrating it to some sort of power that they need. Well, Bayesians are doing something weirdly similar, but the implications are dramatically different. Or can be. There can be good correspondence between these two things or something wildly different. And we'll be going through examples. This is similar, I'm just averaging. And so the question I always ask when people are doing a Bayesian thing is how did they come up with this? Right here. Let me just show you one more thing. And we're done. I think that's okay. I was going to show you the correspondence between a Bayes factor and the posterior probability. And there's a one-to-one equation, one-to-one formula between this and how Bayesian computes the posterior probability of the nulls. Let's come back next time and see what that is, and then we'll start playing with some examples so we can understand the differences. Thanks, you guys. Oh, where's my exams? Let me just call these out to you. You can come up and grab it. If you do have big questions about this, just wait until Friday. Just simmer, let it digest. See Chen? He's not here. Caleb?